So with that, Karl, if you're here, hopefully you're here, please feel free to unmute yourself and share your screen. Welcome.
Thank you very much. Thank you for that lovely introduction. Let me share my screen and then. Great. Well, it's a great pleasure to be here, and also nice to see so many old friends as well. A sort of perverse gift of COVID. I was torn about what to talk about over the next half hour between looking at Markov blankets as one way of studying emergentism and embodiment when the internal states synchronize with the external states. Or focusing on the intelligence part of embodied intelligence. But I've elected to go for the intelligence part and pick up on one of the themes that the first keynote introduced, this notion of intrinsic motivation, and a theme which came back a number of times, particularly in Giantani's and Andy Clark's presentations, the notion of planning and temporal depth and an understanding of the imperatives for behavior and active engagement with the world that looks into the future. So I'm going to focus on the intelligence bit of embodied intelligence, and I'm going to cast that in terms of self-evidencing, briefly rehearse what I mean by that in terms of normative models of action and perception and possibly consciousness and cognition, how it relates to, or how self-evidencing brings to the table some things that would be useful for understanding embodiment in artificial intelligence, and then if we have time, just use a toy simulation just to unpack how the principles work and some of the fundaments of the behavior that ensues. So I'm taking my lead from the notion that all we need to know in terms of explaining and understanding self-organized behavior of a sentient and possibly intelligent sort is that everything in our brains or in our body, and in particular those bits of the body that change the way that the brain and the body samples its sensorium and its eco-niche, everything is just in the service of maximizing the evidence for a artifact or a creature's generative model of its world, M here. So I'm just articulating that mathematically. Everything is in the service of maximizing probability of some observable outcomes, some sensed outcomes, given a model of those outcomes. And I'm just portraying here a number of different takes on that would depend upon your commitments and your training. You could interpret the log of the probability of those outcomes that you're trying to solicit or behave in a way to maximize the probability of those outcomes being elicited as value, the valuable outcomes. And you could look at that from the point of view of reinforcement learning or optimal control theory, or indeed, if you're an economist, expected utility theory. I've cast value in terms of a negative potential that is, in fact, the self-information in information theory, so sometimes referred to as surprisal or surprise. And that's nice, because if we're trying to maximize value or have a normative take on value maximization, then what we're also saying is that we also have an information theoretic understanding of the imperatives that are evinced by self-evidencing in terms of principles of minimum redundancy or maximum efficiency, and indeed the free energy principles. So just noting that the free energy that some people have mentioned provides a bound on surprise or value when cast in this way. In turn, that is also nice because the time average of surprisal or self-information is entropy. So what we're saying is, in self-evidencing, then we are just trying to resist the dispersion according to the second law, which of course is the holy grail of self-organization, particularly in things like cybernetics and synergetics. And of course, if you're a physiologist, it's just homeostasis, keeping physiological outcomes or observable states of the body within viable physiological bounds. I'm going to actually take another perspective though on this quantity, which is the statistician's perspective, namely the probability of some outcomes or observables given a model constituting the marginal likelihood of that model or the model evidence. And then one can spin off the Bayesian brain hypothesis, evidence accumulation, predictive coding, and the like. So that's where I'm coming from. I want to now just drill down on what that means mathematically and just relate it to a couple of things that we've already been talking about. So why self-evidencing? Well, this quantity constitutes the sort of, the core part of this free energy. In machine learning, this is known as an evidence lower bound. Why? Well, because there's a bound here which can never be less than 0, which means that if I maximize f, I am necessarily maximizing a bound on the log evidence, hence self-evidencing. This quantity is going to be interesting later on, but let me just focus in the first instance of why it will be useful from the point of view of, say, artificial intelligence, to maximize the evidence for a model of the world. And implicit in having a model is an explainability. So the quantity, the objective function that I'm trying to optimize, is an explicit functional of a model that renders it inherently explainable. So we have a transparency and explainability and indeed an interpretability for free. That leads on to something quite important, which is optimal Bayesian design. And of course, the interpretation of self-evidencing in terms of a Bayesian brain or a prediction machine, a constructive organ making inferences about its environment. And of course, when you embody or put that in an active context, we have a degree of self-assembly, autopoiesis, and self-teaching or autodidactic capacities, which leads to a principled way of understanding data foraging and epistemics and possibly animal or generalized artificial intelligence. But I want to just rearrange that equation, which is the way that somebody in machine learning might understand this free energy bound. I'm just moving the terms around just to express it in a way that a statistician would be more familiar with it, which is basically the imperative to maximize the accuracy for your explanations or predictions of sensed outcomes, whilst at the same time minimizing the complexity, where the complexity is the degree of belief updating or the amount you have to change your mind in relation to new data, the degrees of freedom you're using up in terms of providing an accurate explanation. And I'm going on about that because I was intrigued by the discussion of complexity either in the brain or in the body, and simplexity and the like. And this is a central notion in terms of self-evidencing, where if not most of, but certainly a substantial part of the drives to maximize this evidence lower bound is in getting the simplest, most parsimonious explanations implicit in your generative model that you can. So that's just, of course, a statement of Occam's principle, and you see that emerging in structure-function relationships in terms of things like modular factorizations in computers, or indeed the brain, where it's known as functional specialization, efficient coding. It also provides an interesting take on bounded rationality. That, it's not a question of just being rational and very accurate. It's a way, it's a special kind, an optimal maximum evidence way of being rational, where you're trying to find the simplest explanation. So it easily accommodates the notion of heuristics via priors inherent in the generative model, namely the probability of some states of affairs in the world generating these outcomes here. It also practically means that when the artifact is behaving in an optimal way in relation to free energy or marginal likelihood, there's some simple physics which says it should be doing it in the most thermodynamically efficient way. So you can invoke the Janinski equality and Landauer's principle to say that if you've got the right solution, or your artifact is self-evidencing optimally, then it will be consuming the least amount of electricity. It will be as small and as simple as possible. So that's the basic, if you like, motivations for self-evidencing cast in terms of maximizing model evidence or marginal likelihood. What I want to do, though, is ask, what would that look like if I had to choose how to use my body to maximize the free energy in the future? And essentially what I'm going to be saying is that if I condition the outcomes yet to be observed on some plan, then accuracy and complexity translate into two things which are which you will all immediately recognize. Basically, they're going to translate into an optimum design and an optimum decision making. So what the story I'm telling here is that self-evidencing just is a mixture of Bayes optimal design in the way that we go and solicit evidence from the world, evidence for our own existence, for our generative model, under prior beliefs about the kind of thing that I am. So here, in this instance, the Bayes optimality is of a decision theoretic sort, that if I choose to do this, then the outcomes are going to be close to my prior beliefs about the kind of outcomes a thing like me will expect to encounter. So I'm just going to briefly rehearse that story by comparing and contrasting conventional RL-like approaches to optimality versus this more general self-evidencing approach. And I normally start this lecture by asking you to imagine that you're a bird of prey and you're hungry. And then I ask the audience normally, what are you going to do? And they normally say, quite correctly, I'm going to search and fly around until I find my prey, and then I'm going to eat my prey. And in that answer, there is buried an important, or several important takes on the kind of functions or functionals that you would use to try and describe good behavior. So we could either assume the existence of a value function of some states of the world that are contingent upon some action or control variable u here. And if this value function of states of the world existed, then I could optimize the value by selecting the best state action policy, pi policy, by selecting the action u for every given state that maximize this value function. And this is known as the Bellman optimality principle. However, just in saying, I'm going to search for my food before I eat it, you're saying something quite profound, because searching is an action that resolves uncertainty. And uncertainty is an attribute of a probabilistic or a Bayesian belief. And therefore, the thing that you are optimizing can't be a function of unknown states of the world. It has to be a function of beliefs about states of the world. So in the sort of Bayesian interpretation, I'm denoting posterior or approximate posterior beliefs about states of the world by Q. So what we're saying is that optimal action depends not upon states of the world, but upon beliefs about states of the world. And we get this sort of functional form here. The other thing that the sort of the owl example shows is that the order matters. It matters whether I, first of all, search for my prey and then eat it, or try to eat it and then search for it, which means that there does not exist an optimal state action policy, but more an optimal sequence of behaviors given what I currently believe about the state of the world at this point in time. And we can articulate that in terms of a path or a time integral of this quantity, which is in fact going to be an expected free energy that Andy and a number of other people have already mentioned, leading us to an optimization of a time integral of an energy function, which in physics is an action. And I'm phrasing it like that because what we've basically got here is a choice between the Bellman optimality principle that would see things like optimal control theory or dynamic processing, deep reinforcement learning, Bayesian decision theory on one hand, or on the other hand, we have Hamilton's principle of least action. or stationary actions more strictly, that is exemplified by things like active inference, and subsumes things like artificial curiosity and intrinsic motivation, that I'm going to cast in terms of optimal Bayesian design that optimally resolves uncertainty about my hypotheses about how my body works and how the world works. It also entails sequential policy optimization and the distinction between observations of a certain world and partially observed worlds. So here's the basic architecture that one has in mind when invoking, and we've seen lots of lovely examples of this. For example, Jantani's illustration this morning. So the basic theme, the embodiment gets into the act here in terms of this sort of reciprocal engagement, this circular causal link between the inside and the outside that Andy was talking about. Mathematically, what one way in which one can describe this is that you get these outcomes supplied by the environment. You use these outcomes to maximize a function of those outcomes and your beliefs under a generative model about states causing those outcomes to form posterior beliefs about states of the world out there. You then use these to roll out effectively into the future under a number of potential policies. So this is exactly the poise over possible actions, or an action space. The action space here is explicitly encoded in terms of sequences of actions or moves on the world, denoted by pi. And each pi you can roll out and estimate the expected free energy, which I've here decomposed into risk and ambiguity, and we'll drill down in that in the next slide. At the moment, we just need to know now we've got a way of scoring each way forward, each one of these possible action, possible policies, possible plans can be scored in relation to our beliefs about the kinds of things that we expect to encounter and the kinds of things that we do with our bodies. And that score can then be used to find the most likely policy, and we select an action from that belief about the most likely policy. It changes states in the world supplies a new outcome, and off we go again in this perception action-like cycle that has this planning and policy selection as an integral part of it. So this is the bit that sort of links the notion of simplicity and complexity to the more prospective aspects of action and planning. So what I've done here is just rewrite down the evidence lower bound, the free energy here in terms of accuracy and complexity. And remember, the complexity is the difference between your posteriors and your priors, the amount you've had to change your mind, which is the energy hungry part of it, and the accuracy here. And just by moving the terms around, we can reconstitute or recover the expression that lends its ELBO acronym, the evidence lower bound, because this quantity is always greater than 0. And here's the expected value. It has a very, very similar form. The only difference is that we're now conditioning upon some possible action or possible sequence of actions. Interestingly, what happens now is, of course, you don't have the observations that would be used to evaluate the free energy, because they're now random variables in the future. So you now have to take your expectation over the prediction of the outcomes in the future, given I'm going to do that, and hence expected free energy. But the form is the same, and I like this because it's really quite revealing. So the complexity becomes risk. The accuracy becomes, or the negative accuracy becomes ambiguity, which means that we're going to choose those things. If we are choosing those things that maximize expected free energy in the future, we are necessarily going to be minimizing our risk and minimizing our ambiguity. And I'll explain what that means in a second. Or we can carve up this expected free energy in another way in terms of the intrinsic and the extrinsic value. And this is the intrinsic motivation. So we have basically both the complexity and the intrinsic motivation, or the expected complexity and intrinsic motivation, as different ways of carving up this underlying imperative for self-evidencing, but self-evidencing where you're maximizing the expected evidence in the future given a particular action. Just to unpack this a little bit for those people in different fields, if I ignore the extrinsic value at the moment, and by which I mean I've got some prior beliefs about the kind of outcomes that I, as a creature, will expect to encounter. If I had no particular preferences, prior preferences, then we're just left with this thing here, which is the expected evidence bound. And this quantity here is just the difference in my posterior beliefs with and without observations that I would get if I pursued this policy. And of course, this is the basis of the mutual information between the consequences and their causes states here that would be expected under that particular policy. If you do visual search or active sensing, active vision, then you may recognize this as the expected Bayesian surprise, basically the amount of information, the epistemic affordance attributed or afforded by this particular policy, the reduction in uncertainty about states of affairs in the world out there in the future, given observations and evidence for those states in the future, if I committed to that particular policy. If I take uncertainty of the various kinds off the table, we're actually going to get back to reinforcement learning or expected utility. But let me just do that carefully. Let's first of all assume that we've got a simple world in which we can sense the state of the world. So we remove the uncertainty about that's inherent in the partially observed aspects of certain models, so that we magically, our outcomes now become the hidden states of the world. We can see everything. In this instance, the S's become the O's, and we're just left, and the ambiguity goes where there is no more ambiguity in the world. We know exactly what's going on. And that just leaves the risk. So what is a risk? Well, it's the KL divergence between what I expect to happen under this policy and my prior preferences. So when I minimize risk, what I'm doing is I'm choosing those policies that will lead to states of the world or their outcomes that a priori I prefer. So I'm trying to minimize the degree of divergence or difference between, again, posteriors about future outcomes and priors over future outcomes. So very, very closely related to complexity, the complexity cost, but now we're talking about the future. If I remove the final kind of uncertainty from the table, what we're left with is effectively, and the final kind of uncertainty is that the uncertainty due to different actions, relative uncertainty, just disappears. I'm just left with this thing here, which I set up in the first slide as being really a version of expected utility theory, where the expected or extrinsic value is just the expected value or the log probability of preferred outcomes under what I anticipate to ensue given a particular, well, in fact, given all policies or actions here. So what we've done here is derive from the simple notion of self-evidencing the service of garnering evidence for your own existence as implied by your model, your embodied model of the world, and carving it up into two different aspects of Bayesian good behavior. First of all, I'm going to commit to those behaviors that would, or choices that have the greatest expected value. And in statistics, that's known as making Bayes optimal decisions under some loss function. But here we're casting the loss function or the utility function in terms of a prior preference. And then we're just adding to that effectively the information gain that ensues from pursuing a particular policy, and together they constitute the expected free energy or the expected evidence afforded by a particular policy. So I'm going to close now just by very quickly taking you through some embarrassingly simple simulations. Having looked at the beautiful simulations this morning, we are nowhere near able to scale up to that level of sophistication. However, I think they're still illuminating, in the sense that there's a certain simplicity in what I'm saying, even though some of the maths may look a bit complicated. I'm not going to go through this in any detail. I just want to show you the kind of behavior, the sort of behavior that is mandated under this optimization of expected free energy. We normally use Markov decision processes, sort of discrete state space models of a world, graphically cast in terms of transitions from one state to the next point in time, generating outcomes of the likelihood mapping, where the transitions are dependent upon a policy, BUs encoding the probability transitions. And then we have interesting, well, the policy clearly depends on the prior preferences encoded by this preference or cost function here. We also have, in many of the simulations, the precision of our beliefs about policies. And I just mentioned that because that's the W in John's talk that sort of tunes the hierarchical depth or the ability to learn versus to teach, depending upon the confidence that a priori you place in your inactive policies when interrogating or querying the world. A couple of hyperparameters about initial states. And when we plug this very generic form for the generative model into standard elbow or free energy optimization schemes, we get a series of belief updating equations that look very much like what the brain does. And indeed, we know that because of all the simulations and interpretations, process theories that we've already witnessed this morning and in the literature. So, there aren't many unknowns here. We just don't know about the state of the world. We don't know what we're doing, and we don't know how confident we are in what we're doing. We actually also don't know the parameters of the model itself. The likelihood mappings and the transition matrices. So those can be learned. So we just have perception, which is resolving uncertainty or inferring states of the world, policy selection, so having the right poise, if that's correct, abuse of Andy's philosophical term, on the space or possible actions, and also having a kind of second order belief about our beliefs about those actions in terms of the confidence or the precision that incidentally looks as if it's encoded by dopamine in human brains. Then we have learning of the unknown structure of the world that would be of particular interest from the point of view of the sort of the embodiment part of this equation. And then action selection is just selecting an action from my beliefs about what I do. And when I simulate that, and I'm going to simulate that by applying those equations to a little mouse who has to solicit a baited reward from the right or the left arms. It only has two moves and has to stay in one or the other arm once committing to one of those arms. But it has a choice of using up one of its moves to go and get an instructional cue that will tell it definitively whether the reward is there or there. So this little rat has the choice of taking a gamble, and it could be 50% correct, and staying there, or spending one of its exploitative moves in an exploratory sense to go and resolve uncertainty about the world, and then go and secure the cheese. And of course, this is set up, this sort of two-step paradigm is set up just to demonstrate, even though the expected utility of both policies is identical on average, that the self-evidencing creature will clearly go and resolve its uncertainty, responding to the epistemic affordance or the intrinsic motivation, go and get the cue, and then go and enjoy and exploit its knowledge by going to the arm that is baited. And indeed, that's what the agent does. But what this simulation is showing is a systematic and principled and completely non-stochastic. This is a deterministic optimization of expected free energy, which means that if you actually introduce a predictability and a structure and a consistency to the world, which we've done here just by leaving the reward on the left arm perpetually after the first couple of moves, then the creature, the rat, will come to learn this. And therefore the salience or the novelty of the uncertainty resolving cue slowly wanes. And there is no uncertainty after a while because the rat knows that the reward is over on this side. And therefore the epistemic affordance, the explorative drives, the intrinsic motivation for going to the conditioned stimulus or the instructional cue starts to disappear. And at some point, when the intrinsic and the extrinsic, when the intrinsic value or motivation falls below the pragmatic or the extrinsic value, it'll just switch to a different kind of behavior. And this is incredibly systematic, and you see this in many, many simulations and indeed in real world situations where your first imperative is to resolve uncertainty about this particular world, this eco niche, this body. And when you've done that, you start to then turn to your prior preferences because there's no more uncertainty to hoover up. So by move 20, the rat just goes straight there quite happily and will do so forever if nothing else changes. This is the final slide, and I've got 30 seconds left. So I put this here just to remind myself about that initial ambivalence about whether to talk about sort of the emergence of lifelike behavior from first principles, or whether to talk about the sort of the mechanics of planning and deep generative models of my own action. It would be nice to actually connect the two perspectives, and I'm just putting this up as an outstanding challenge and the frame in which I think that challenge can be met. I won't go into this, but other than to, if anybody's interested, provide a sort of starting point for discussion. So here's what we've just been basically saying. We can understand the right kinds of behavior in terms of selecting the right possible actions, and what are the right ones, where they're the ones that underwrite our self-evidencing, that minimize risk and ambiguity, and they have this functional form. There's another way of understanding the universe in terms of non-equilibrium steady states that are normally described in terms of integral fluctuation theorems if you did chemistry or physics. And they have a very similar structure in terms of articulating the probabilistic development of states and outcomes, consequences upon different states in terms of K-on divergences to provide bound or inequalities that underwrite much of statistical thermodynamics. Interestingly, you can use the integral fluctuation theorems to derive this if you make one particular assumption or commitment, one small move here. And all I'll say about this is it hasn't actually been done yet, but it does involve some probabilistic relationship between the probability of a path of action into the future and the ambiguity or the negative entropy of outcomes given their causes. So again, linking action and uncertainty in an intimate way, which may be the key for understanding the kinds of systems, i.e. creatures like us, that distinguish ourselves from things like viruses or other self-organizing systems that don't plan. Anyway, I'll leave the last word with Einstein. Everything should be made as simple as possible, but not simpler. And all that remains is for me to thank those people whose ideas I've been talking about. And of course, thank you for your attention. Thank you very much indeed. I'll stop my sharing now.
Thank you very much, Karl. I'm sure the 348 participants, if they could, they would unmute and join me in thanking you. There's a couple of questions arriving in the Discord. So before we get to one or two questions, I'd just like to ask the organizers if they could help connect Professor Friston with the Discord if he's not there already. There's a question from Dana Damien. Beautiful theory, thank you. Does this theory also explain the emergence of belief in the first place?
In an elemental way, yes. So that would be part of the story that I couldn't tell. So if you just take any system that has self-organized to some kind of non-equilibrium steady state, so it persists, there are recognizable characteristics, and then you partition that system into inside states that constitute the inside of a system and the environment, and then they're enshrouded by blanket states. This is a Markov blanket partition. Then you can use the necessary properties of non-equilibrium steady states, solving the density dynamics, to show that there is an information geometry where the physical inside states come to parameterize Bayesian or probabilistic beliefs about the outside states. And that licenses then an information geometry, which is a geometry of belief states. So if you permit me to interpret beliefs as Bayesian or probabilistic beliefs, conditional probability distributions, then mathematically you're saying, is there an information geometry there? And what I would say, yes, there is, under the condition you've organized to a non-equilibrium steady state.
Great, thank you. Again, more questions arriving. There's a question here in Zoom chat from Andy. If minimizing expected free energy delivers simple planning, what delivers deliberate planning? That seems different yet related.
I think the distinction is a very subtle one, and we don't have time to get into it because it is a really interesting question. So notice that I was just carving this functional, this sort of expected free energy model evidence into two bits that linearly decompose, because we're in log space, into sort of an information gain effectively, and a pragmatic or expected utility term that could be resolved independently. So you could argue, well, look, yeah, that's fine, but that's not really resolving uncertainty about what matters to me in relation to my prior preferences. Yeah, so I'm just resolving all uncertainty, irrespective of what I actually think I should be, the kinds of things I'm going to solicit. So if Andy's asking that question to ask, well, when does it get more interesting? One could algorithmically say, well, you have to move to sophisticated inference where you actually have to, instead of just resolving uncertainty, you have to actually encode what would I believe if I knew that? And what would those new beliefs mean as I work towards my preferences? It's not difficult to do. It's basically a probabilistic generalization of the Bellman recursion. However, I'd actually say you probably don't need to do that, because remember, although these two bits of the good ways to choose your policies are linearly separable, they're linearly separable in log space, which means you're actually multiplying. So what you are saying in terms of probabilities, I am choosing those policies that have the greatest epistemic affordance, given that they afford outcomes that I prefer. So I think there's actually built in for free a certain sort of deliberation there, in the sense that, conditioned upon resolving uncertainty, there has to be an aspiration to the goals that are written into the prior preferences.
Great, thank you. We have some time for discussion at the end of the plenary session, so I'm going to use my host privileges here and ask you one last question from Discord. How does free energy deal with groups of agents and a common belief among the group? Will it promote agreeing with the group over further exploration of the environment?
Yes, it does. It promotes cooperation and generalized synchrony. So mathematically, that generalized synchrony basically affords a predictability of two agents in a dyad, or in fact a multi-agent context. So if the whole game is to minimize surprise, then the best solution is to basically make you exactly like me and make me exactly like you, and then our discourse will be in perfect synchrony. We're both mutually predictable, and our joint free energy will fall. So it's all about finding harmony in groups and a shared narrative, a common ground. And from that, you can spin off all sorts of hermeneutic interpretations, and indeed, you know, the imperatives for language in terms of cultural niche construction under this sort of variational frameworks. And that would have been a third lecture, which you can't do everything in half an hour.
Certainly can't. Thank you so much, Professor Friston, on behalf of all the participants here for a fascinating and thought-provoking presentation.